5月1号还有一课。
哦，5月1号还有
一个钟头的课。对，
哦，
因为我4月7号，我那个取消了1个钟头，所以要补。
好，
因为总共是36小时。
那期中考也会进行课程吗？
没有。
期中考那周没有？
没有，因为我已经有3个习题3个作业，然后这个礼拜会给他们最后的1个作业，那就这样子。
所以期中考是
他是问期中考那一周有要上课吗？
期中考我不知道，
就是其他人
那是几月几日？
应该有要上课吧？
我觉得没有关系，
应该还是有要上课吧？
是几月几日？期中考？
应该是看每个科系他们自己定的时间，对不对？应该这个在下周吧。
反正是第9周就是。
我意思说他要来进去就
没关系，就上。
22号那周是
20。那你们别的课有没有期中考？OK， 反正我们没有期中考，我们只是4个作业。
好
呀，所以我想期中考的时候，我们就继续上课这样。
好。
然后到5月1号，5月1号是只有1小时这样，那是最后1小时。好。Okay, I first want to finish the proof of the theorem that the equivariant cohomology of a locally free action is U torsion. So now we have this formula, okay? 1 is equal to something. And I just want to show that this something is exact, okay? So let's see, let's compute dx of this term, d phi over u. Okay. Now, by definition, you just compute dx of d phi and put it over u. Okay, so that's the definition of dx u, which now I write as dx. It's just the notation, right? And then dx of d phi, okay, that's d of d phi minus u ix d phi. Okay? So that's the definition of dx. Okay, now dd is 0. Okay. Ixd, how do you calculate Ixd phi? Yeah, you can interchange them because Ixd is Lx minus Dix. But Lx of phi is 0 because phi is invariant. Okay? Lx of phi equals 0. And so this is going to be 0 minus u, well, plus dix phi. Okay. I pick up a minus sign from this. And then I know that ix phi is 1, so this is actually 0. Dix phi is d of 1, and that's 0. Okay? So that says that d phi over u is a cocycle. Okay? And when you multiply cocycle by a cocycle, you again get a cocycle. So all of these terms are cocycles. Okay. So thus one plus d phi over u plus d phi square over u square plus d phi to the n minus 1 over u to the n minus 1 is a dx cocycle. Okay? And so here you have a cocycle times a coboundary. This is dx, so dx phi over u is dx of phi over u. Yeah. And so minus dx of this whole thing times phi over u is 1. Okay? Right? Because if you apply the anti-derivation rule, so dx of this first term is 0, okay? And then you have this first term times dx of this. Right. So we'll get this. Okay? Yeah. So all of this is to write something as alpha so that dx alpha is 1. Okay, so now let alpha be equal to minus 1 plus d phi over u plus d phi to the n minus 1 over u to the n minus 1 times phi of u. Okay? Yeah, this has even degree. This has odd degree. Let alpha be that element, then dx alpha is 1. Okay? And I explained earlier that if you can find an alpha so that dx alpha is equal to 1, then the cohomology of the complex localized at u is 0. Okay? And this is the localization of the equivariant cohomology of M. Okay? All right, so that proves the theorem. Okay? So let's state the theorem again. So therefore, we have the theorem if S1 acts locally freely on M, then the equivariant cohomology is U quotient. Okay? Yeah. Okay, now I'm going to prove what's probably the most important theorem about equivariant cohomology so far. Okay? Well, the equivariant Theorem theorem is very important, but we didn't prove it. I will prove it at the end. Now I'm going to prove a theorem that's called the Boreal localization theorem. Okay? For a circle action. So the Boreal localization theorem says that if S1 acts on a manifold M, with fixed point set F, okay, then the inclusion of F into M induces a restriction in equivariant cohomology So then the natural restriction map okay, it's not quite an isomorphism, but these are all R of U modules, so you can localize with respect to U. So if you localize with respect to U, then this is an isomorphism. It's an isomorphism of algebras. Now, what it says is that you can get a lot of information about the equivariant cohomology of the manifold from just the fixed point set. Okay?
Each is a manifold.
Pardon?
The fixed point set is a manifold.
Yes, and that's another thing we have to prove. So today, I won't quite prove the theorem, but first I will prove a few general facts about equivariant cohomology, like the fact that F is the fixed point set is a manifold, you know, and like a closed subgroup of the circle. If it's not the whole circle, it's discrete. You know, I have to prove a few general facts, and then we can prove the theorem. Okay. So if the action has just some finite number of fixed points, you see, then it places a lot of restriction on the equivariant cohomology of M. Okay, so what we really want to know is the equivariant cohomology of M without the localization, right? Yeah, so yeah, eventually we'll get there. Okay, yeah. And because this is an isomorphism of algebras, you see, and this is fairly simple. If M is just a couple of points, you see, then you can get the ring structure on the equivariant cohomology of M. Okay? So that's how we are going to get the equivariant cohomology of the sphere under the action of S1. Okay? Okay. So this is an isomorphism of algebras. Okay? Over R of U localized at U. Okay. Yeah. So this lecture is titled General Facts About Equivariant Cohomology. So let's first study the fixed point set. Okay, so I'm first going to prove that the fixed point set is always closed. The fixed point set of group action now, I think right now I just have to assume a continuous group action. On a topological space X is closed. It's closed in X. The fixed point set is closed in X. Okay, so proof. So let P be in the fixed point set. Then, no, let's see. I want to let P be a limit point in the fixed point set. Be a limit point of the fixed point set. Okay? And we just have to show that it's in F. Right? A limit point means that there is a sequence Pn in F such that the limit of Pn is P. Okay? And so because Pn is in F, then for all G in G, G dot Pn is Pn. And because the action is closed, it is continuous, if Pn goes to P, then Gpn converges to Gp. And so, Yeah, so now GPN is Pn, so Pn converges to P, and that's equal to GP. Okay, therefore P is a fixed point. So P is in F. So every limit point of F is in F. That means F is closed. Okay? Yeah. Now, let me see. Can I just assume that X is a topological space? I think in order to talk about limits of a sequence and for the limit to be unique, that topological space has to be Hausdorff, right? So I think I do need Hausdorff here. Yeah. Okay. It doesn't matter. Eventually, we will only work with manifolds. So a manifold is Hausdorff. Okay. But yeah, so I think for this proposition, we do need to assume that the topological space is Hausdorff. Okay. So the fixed point set is closed, and then next I want to show that the fixed point set of a Lie group action on a manifold is a manifold. Oh, but I actually have to assume that the Lie group is compact. So theorem. If a compact Lie group acts smoothly on a manifold N, then its fixed point set F is a regular submanifold. N. Okay. So a regular submanifold means that it's a submanifold that's locally defined by the vanishing of some equations. Okay. So locally it will look like this. It's locally defined by the vanishing of some coordinate functions. So let's just say locally it looks like Rn. Rk inside Rn. Okay? I mean, you have immersive manifold also that don't look like this locally, right? For example, the irrational, the line with irrational slope in a torus. So a regular submanifold looks like that, but a line with irrational slope in the torus, it locally looks like this, and it's dense. So this is an immersive manifold. Okay? But this theorem says that the fixed point set of a smooth action looks like this. This is very nice, regular submanifold. Yeah, regular submanifold is the same as embedded submanifold. Okay. Now the reason we need a compact V group is that if you have a compact V group, then you can put an invariant metric on the manifold. Okay? So since V is compact, since G is compact, we can put a G invariant Riemannian metric on M. Okay? And once you have a Riemannian metric, then you have what's called the exponential map in differential geometry. Okay? So for a point x in M, consider the exponential map. Okay, so the exponential map it's a map from the tangent space, so of M. So let's say here is a tangent space of M. Okay. Now, if you pick a small tangent vector, then there is a geodesic, okay, that starts at X and it goes somewhere. Okay? And if the vector is small enough, then this geodesic will be defined for a certain interval. Okay? You can always make sure that by making the vector small, that geodesic is defined for at least 1 second. Okay? And then when you go for 1 second along that geodesic, that point that you get is the, so if this is V, that point is the exponential map of V. Okay? That's how you define the exponential map. Okay? You take a geodesic, go for 1 second. Okay? So there's some small neighborhood here, V, on which the exponential map is defined. At X. And in differential geometry, you can calculate the differential of the exponential map, and you find that it's the identity, so it's non-singular. If the differential is non-singular, that means that it's a local diffeomorphism. So by making this neighborhood very small, you can make sure that this is actually a diffeomorphism. Okay? So the exponential map goes from some small neighborhood V in the tangent space to a small neighborhood U in M, so that it's a diffeomorphism. Okay? Mm-hmm. Consider the exponential map. Okay? So by choosing V sufficiently small, the exponential map from V to U is a diffeomorphism. Okay, now, but the tangent space is a linear space, so it can be identified with Rn. And so the inverse of the exponential map maps U into an open subset of Rn, so that means it's a coordinate map. Uh-huh. So we can use the inverse of the exponential map as a coordinate map. Okay, and then now in differential geometry, you have a theorem that says if you have an isometry, okay, if you have an isometry between two Riemannian manifolds, then there's a commutative diagram. Oh, sorry, it doesn't go like this. Here I'm going to use I'm going to choose I'm going to choose V to be G invariant. You see, okay, I'm getting ahead of myself. So, yeah, so the tangent space, okay, it has a metric, right? Because we are on a Riemannian manifold M. That means every tangent space has an inner product. Uh-huh. Yeah. So the tangent space has an given inner product and because the tangent space is a vector space, you can treat it as a Riemannian manifold, right? Where at every point you have this inner product. So this makes the tangent space into a Riemannian manifold. Okay? And G acts on the tangent space by, so G dot a vector V is, you have, because G acts on M, yeah, so because G acts on M, the differential will act on the tangent space if X is in the fixed point set. Okay? So now I'm going to make X in the fixed point set. Then LG lower star, it will send V to the tangent space at Gx, which is X. Okay? And therefore G acts on the tangent space. Okay? So this is again in Txn, since G dot X is X. Yeah. So now I have an action of G on the tangent space, and then now here I choose a small u. I can choose that u so that it's G invariant. So no, I choose V. I'm sorry. I choose V in the tangent space. So we can choose V in the tangent space so that V is G invariant. Okay? So, yeah, I want to make sure that G takes V to V. And how do I do that? How can I choose V so that I know that it's invariant under the action?
Integrate over G.
Pardon?
Just arbitrary the vector and then integrate the LG, the push forward of V over G.
No. I want to choose like an open set. That's G invariant, not just one vector. That's G invariant. Now, remember that this inner product is this G invariant Riemannian metric, okay?
So the length of GV will be equal to V, and we just choose the open ball.
Yeah. See, if you choose an open ball, for example, if V is an open ball, okay, with center the origin and radius epsilon, and you have any vector in V, then you see when you translate it by LG, okay, so the length square is LG dLG V, and because this is an invariant in a product, this is equal to VV. Okay? And so if V is in this open ball, then its length square is less than epsilon square. And so the image is also in this open ball. Okay? So if you choose any open ball around the origin, it will be G invariant. Okay? So that's any open ball, center at the origin in V is G invariant. Okay, so here I can choose a G invariant open ball. Then, any open ball center at 0 in the tangent space is G invariant. Okay, and so we choose a sufficiently small open ball to be V. Okay. It has to be sufficiently small so that the exponential map is defined on it. Okay. And then you have V. Okay, now LG star will take V to V because it's invariant. And then the exponential map takes V to U, and that's a diffeomorphism. Okay? And exponential map takes V to U, and that's a diffeomorphism. Okay? And from differential geometry, there is a commutative diagram. Okay, where this map here is LG. Yeah, LG LG is an isometry, okay? Because the the Riemannian metric is G invariant. So an isometry just means that, right, LG lower star preserves the inner product. And so that's what G invariance gives you. So I will say because LG is an isometry. Okay, so that means LG star of any vector W and say V is WV. And that's true because the Riemannian metric is G invariant. Okay? So if you have an isometry, then you have a commutative diagram like this. Okay? And now, so under this commutative diagram, the fixed point set is something that goes from the set to itself, right? So let's see. Okay. So let F be the fixed point set of G on M. Okay, then F intersect U is the fixed point set of G on U. Okay? Yeah, LG takes U to U. And the point that's fixed is F intersect U. Yeah. Now, F intersect U so this is a diffeomorphism. So it's going to correspond to the fixed point set of this. Yeah. Okay. Exponential inverse of F intersect U is the fixed point set of V, G on V. Okay. Now the fixed point set of G on V, that means it's fixed under LG star for all G. Okay. So the subspace, the set, the subset of V fixed under LG star is, what is the subset that fixed under LG star? It has another name because LG star, that's a differential, so it's a linear map. So if it's fixed under the linear map, it's, what do you call that? It's this, right? It's this set. And if you have a linear map that takes V to V, then V is, it's in the eigenspace with eigenvalue 1. Okay? So this is, it's V intersect the eigenspace of LG star with eigenvalue 1. Okay, so it is V intersect, the eigenspace is a linear subspace. Linear subspace. And let's call this, let's call that space EG. Okay, so EG is the eigenspace of LG star. And so now the fixed point set is fixed under all G. So the fixed point set of G on V is V intersected with, you need to be fixed under all G, so it's the intersection of EG for all G in G. Okay? And the intersection of a linear subspace is again a linear subspace, so this is V intersect a linear subspace. Okay? And that means it looks like this. You have an open ball, that's your V. And then you have a linear subspace. And that's your fixed point set. Okay? But this is diffeomorphic to F intersect U. So F intersect U, so this is V, an open ball, in the linear subspace. And so F intersect U is going to be U. Now U is not necessarily an open ball, it's just some open set. And then you have whatever that corresponds to that linear subspace under a diffeomorphism. So it will look like this. So that's a picture of a regular submanifold. Okay? Hence, F locally looks like this. So F is a regular submanifold of M. Okay? Yeah. So I'm going to stop here. And so, so today we just proved that the fixed point set is a regular submanifold. Okay? And next time, we'll prove a couple more general facts. Then we will prove the Boreal localization formula, theorem. And then that will give us the ring structure of equivariant cohomology from the fixed point set. Okay? And so then we will get the ring structure on this example of the two sphere, okay, under rotation. Yeah, because the fixed point sets are just 2 points. Okay, so I will see you on Friday. And so if you want